we're going to continue talking about second-order linear differential equations. And I'll repeat the existence and uniqueness theorem. This is our main theorem that tells us when we're guaranteed to have a unique solution to an initial value problem. This was mentioned in a previous video lecture, but it's going to be fundamental to what we're talking about today. So we consider this initial value problem where we have a differential equation. This is a second-order linear, not necessarily homogeneous differential equation with initial conditions of this form. You specify the value of your solution function y at some point t naught. Y naught is arbitrary here. And you specify the value of the derivative of the function y at that same point t naught as some other arbitrary value. Here, p, q, and g, we'll assume they're continuous on some open interval I that contains, I should have written this, contains t naught. Now, what is the conclusion when we have that? If we have such a nice initial value problem, the conclusion is there's a unique solution y equals phi of t, which is valid on the entire interval I. And when I say a unique solution, that's a solution to the differential equation, which also satisfies those initial conditions, the initial values. Now, we've already introduced this linear operator L of y. That's y double prime plus L of y is y double prime plus p of t times y prime plus q of t times y. Remember, L is linear. What does that mean? It means L of y1 plus y2 is L of y1 plus L of y2, and L of a constant c times y is just c times L of y. So L is what we call a linear operator. And because L is a linear operator, it's easy to see that if we have any two solutions, y1 and y2, to the homogeneous equation, L of y equals 0, that's the same as y double prime plus p of t y prime plus q of t y equals 0. If we have any two solutions to the homogeneous equation, then any linear combination of those two solutions, c1 y1 plus c2 y2, here c1 and c2 are any constants, will also be a solution. Here's the important question. How do we know, let's say, for example, that we have two solutions to this differential equation? How do we know if the general solution is exactly a linear combination of those two solutions that we have? If I tell you two solutions to this homogeneous equation, are all the solutions of this form? Are there other solutions that are not of this form? This is an important question that we have to ask. And we can answer that question by trying to solve arbitrary initial value problems. So let's say we're given this should, I apologize, let me change this here. This should be 0. We have a homogeneous linear second order differential equation with initial conditions. And let's say that we have two solutions y1 and y2 to the differential equation. The differential equation is of the form L of y equals 0. That's this differential equation. Now, if I want to satisfy that differential equation with these initial conditions, then what we have to do is find the function y, or what we would like to do, I should say, is find the function y, which is a linear combination of these two solutions that we have, which also satisfies the initial condition. Maybe we can, maybe we can't. Well, if we can force y of t naught, that's this, y of t naught is this one. If we can force that to be y naught, and if we can force y prime of t naught, that's this one, to be, this should be y naught prime. So let's put that, I'm fixing these things here. If we can force both of these equations to hold, then we'll have a linear combination of these two solutions, y1 and y2, which really will solve the initial value problem. And by our existence and uniqueness theorem, that will be the unique solution to this initial value problem. Here's the question. When will there be a solution here? And remember, when I say a solution, I mean a solution to these two equations. And we want to, what we're doing is we're trying to find values for C1 and C2 that make these two equations hold. Once we have our two solutions, y1 and y2, and we know our initial point t naught, and we know these initial values that we want, all of these are just constants. These are now fixed. All of these are fixed, these are fixed, this and this. And this is just two linear equations in these two variables. C1 and C2. And from linear algebra, which I know you've all taken, at least Math 206 or the equivalent, we know ahead of time when we can expect to find a unique solution to two linear equations and two unknowns. One condition for that is that the coefficient matrix in this case, the coefficient matrix is this matrix y1 of t naught, y2 of t naught, and down here we have the coefficients y1 prime and y2 prime. A condition for the existence of a unique solution to these two equations in the two unknowns C1 and C2 is that the coefficient matrix must be non-singular. In other words, has determinant which is not 0. As long as the coefficient matrix is non-singular, we are guaranteed to be able to solve these two equations for C1 and C2, and thus find a linear combination of y1 and y2, which will be the unique solution to the initial value problem. If the coefficient matrix is singular, if this determinant is 0, then in general, unless you're really lucky with y naught and y naught prime, in general there'll be no solution here, and you will not be able to solve the initial value problem just with a linear combination of y1 and y2. So in order to really address this, we define the Wronskian. The Wronskian of two functions y1 and y2 is defined to be y1, y2 prime minus y1 prime, y2. And notice that the Wronskian, it's going to be a function of t, and as a function of t, it's exactly the determinant of this matrix that we were talking about before, the matrix y1 of t, y1 prime of t, y2 of t, and y2 prime of t. So the Wronskian is defined to be this determinant, y1 times y2 prime minus y1 prime times y2. That's the Wronskian. And so from what we said before, if the Wronskian evaluated at t naught, because we had all these coefficients were y1 of t naught, y1 prime of t naught, y2 of t naught, and y2 prime of t naught. If the Wronskian at t naught is non-zero, then we can solve this system of two linear equations and two unknowns. We can solve it for C1 and C2. And thus, we'll have a solution to our initial value problem for our homogeneous linear differential equation. which is a linear combination of our two given solutions, y1 and y2. Because the Wronskian tells us exactly when we can solve any initial value problem, we call two solutions, y1 and y2, to this homogeneous linear second order differential equation. We call them a fundamental set of solutions exactly when the Wronskian is non-zero. What does this mean? Well, if the Wronskian, and remember this is a function of t, this should be if, the Wronskian is as a function of t is never zero, then for any initial condition, initial condition would look like this. Say y of t naught equals y naught, and y prime of t naught equals some other value, y naught prime. This will be y naught. For any initial condition you throw at me, I'll be able to find a solution to the differential equation with that initial condition, which is a linear combination of y1 and y2. So the initial value problem will have a solution of the form y equals c1 y1 plus c2 y2. In other words, we say the general solution to y double prime plus p of t, y prime plus q of t, y equals 0, is the set of functions y equals c1 y1 plus c2 y2. Here c1 and c2 are just arbitrary real numbers. So we'll then have completely solved this linear homogeneous second order differential equation, and here are all the solutions. Remember, we get this situation when we find two solutions to the linear homogeneous differential equation whose Wronskian is non-zero. They will then constitute a fundamental set, and we have a complete solution.